If a relation pairs element A of its domain to element B of its range, the inverse relation pairs B with A. So if you have an ordered pair A comma B of a relation, then B comma A is in its inverse. If both relations happen to be functions, the regular one and the inverse, we call them inverse functions. Remember, not all relations are functions, but all functions are relations. So here are four ordered pairs. If I were to say what is the inverse of these ordered pairs, you find them simply by switching them. So the first ordered pair would become -3, 2. The next ordered pair would become 6, -5. The next one is 8, 0. And the last one is 1, 4. An inverse simply switches the domain and the range. Remember, the domain are your x values. They're your inputs. And your range are your y values. Those are your outputs. So in problem 1, we want to find the inverse of relation S. Relation S has these ordered pairs that we'll give you as a table this time instead of as a set of ordered pairs. Well, in order to find the inverse, all you have to do is switch x and y. Now that doesn't mean that you put y first and then x. It just means that all the y values become the x values and all the x values become the y values. That's all an inverse is. But that may not mean anything. So let's look at the graph of an inverse. So now in this next part, we're going to graph relation S and its inverse. So looking back at the ordered pairs, we're going to start by graphing 0, -1, 2, 0, 3, 2, and 4, 3. So 0, -1 is here. Now I can't remember what they were. 2, 0 is here. 3, 2 is here. And 4, 3 is here. I'm going to do the inverse in green. So the inverse was at -1, 0, 0, 2, 2, 3, and 3, 4. Now, what I want you to notice about that is there seems to be a line that I could draw down the center here, about which those ordered pairs are symmetric. Well, that's not any line. That's a special line. It's called the line y equals x. The line y equals x is the one that goes through 0, 0, 1, 1, 2, 2, 3, 3, -1, -1, -2, -2, -3, -3. So we also say that an inverse, other than switching your input and output or domain and range, is a reflection over the line y equals x. Now let's talk about finding the inverse of an equation. So in order to find the inverse of an equation, we're going to do it this way. We're going to solve the equation for the other variable. Sometimes they tell you to switch x and y and then solve for y. So sometimes they say flip-flop x and y and then solve for y. Well, in order to solve that equation for y, you would first need to subtract 4. And then you would need to divide by -3. And this would be the equation of the inverse. Sometimes we just tell you to solve for the other variable. So solve for x. So you would subtract 4 and you would divide by -3. both of these equations really are the same exact thing. The textbook does a little something different with this equation. It doesn't like to have negatives in the denominator, so it multiplies everything by -1. When it multiplies everything by -1, it gets this, but I'm not particular about that. Now, the reason I'm not particularly fond of switching x and y and solving for y is because this is a very generic situation in which we find an inverse. A lot of times we're finding inverses of actual equations, like equations you learned in geometry, or, the equation of converting Fahrenheit to Celsius or vice versa. And we don't really want to switch the input and output. It's really the same as just solving for the other variable. Now let's do it again with something that's nonlinear. Part A was linear. This is quadratic. So in order to solve for the inverse, the way the book does it is it switches x and y, and then it solves the equation for y. So they would add 5, and then they would square root both sides. But because it's an equation, I told you that you need to stick the plus or minus sign in front of the radical. Now let's talk about the graph of an inverse when you're talking about an equation rather than the ordered pairs. Now, however, I'm going to give you some options for doing this. So let's look at the graph of y equals x squared minus 1 and its inverse, which happens to be y equals plus or minus a square root of x plus 1. If you want to prove that that's the inverse, you can. You don't have to. The graph of y equals x squared plus 1 is the parent function y equals x squared that's been transformed down 1. So that means that the vertex is at 0, -1, so it must go through those points and these points. Why does it matter what ordered pairs it goes through? Because now when you want to find the inverse, the easiest thing to do is to take those 5 ordered pairs and reverse them. So on the original graph of y equals x squared minus 1, this particular graph goes through -2, 3, -1, 0, 0, -1, 1, 0, and 2, 3. So the inverse must go through 3, -2, 0, -1, -1, 0, 0, 1, and 3, 2. So now I'm going to graph those ordered pairs. 3, -2 is here, 0, -1, -1, 0, 0, 1, nope, that's not right, 0, 1, and 3, 2. And you'll see that the parabola opens off to the side instead of up and down. Remember, we said a few moments ago that an inverse is a reflection over the line y equals x. Think about a sheet of paper, and you were to fold this over the sheet of paper. Then the red graph, if you fold it along the green dashed line, would lie on top of the purple graph. Now, the thing about the purple graph is if you were going to go put this in a graphing calculator to look at it, you would actually have to look at 2 different functions. You would have to do y1 is equal to the square root of x plus 1, but then you would have to graph in y2 equals negative square root of x plus 1. Because remember, the plus or minus sign means it's really 2 separate equations. They just connect to make one graph. This is kind of a precursor as to what we'll be doing in the next topic.